All right, great. Thanks for that. Sorry for the delay there. All right, so announcement. So there's I think only one Canvas activity left. This Canvas activity L. This is I think due in about a week. It's the last kind of new Canvas activity, and then after that, the Canvas activity that comes after that is purely a midterm review Canvas activity, and so that Canvas activity M will be due before lecture M. I think it's already available. It's a 30-ish point Canvas activity, so it's worth 3 times as much as a normal Canvas activity, but you can take it as many times as you want, and it just samples from all the previous Canvas activities. And so it's a good way to increase your buffer if your Canvas activity score is down, while also reviewing for, like I said, midterm, but the final exam, so that it'll prime you for lecture M, which will be our final exam review lecture. Homework J2 has been out, and I sent some hints about that. If you didn't see those, check the discussion or the Slack, and there's some hints on how to modify this, at least for I think the hardest part of the modification is coming up with the logic to prevent there being more than one outstanding order at a time. So if you're having trouble figuring out how to start that, then check out some of the hints that I posted to the discussion as well as the Slack. So this says no more lab experiences, but because of Veterans Day, Lab 10 is formally this week. Definitely encourage you to take a look at Lab 10. It's as most labs are out of 30 points, and this one's out of 30 points, but there's 50 points possible. So it's basically 2 labs bundled into one, and if you do all of it, you have a possibility of getting 20 extra bonus points for your lab credit. So take a look at Lab 10. I also think Lab 10 has got some really useful things, about both ARENA, in how to build models, as well as how to do the data analysis and the optimization. So you'll get more exposure to things like the process analyzer, OptQuest, batching, sequences. There's just a bunch of really useful things that you can do inside ARENA. Otherwise, final project. So all of your input modeling reports have been returned. I think there was only one input modeling report that I thought had significant issues, and I mentioned that in those comments. Everybody else's, I comment on everybody. So look at your input modeling reports, look in the comments in the document, as well as the comments in the rubric. So when you fill out the rubric, you can make comments for every category of the rubric, and then also the comments, the general comments for the grading. So I tried to put most of my comments in the document, but there will be additional comments in the rubric as well. And most everybody, I think, is heading in the right direction. There were a lot of coffee shop drive-throughs, more than usual, strangely enough. Maybe that's just due to kind of COVID and people wanting to stand outside of coffee shops instead. My general advice there is to keep in mind that the queue between the ordering window and the pickup window is a finite length. I have a video on Canvas about how you can use the hold module in order to cause entities to queue up sort of upstream when there's a queue that's full downstream. And so it shows that when you have serial processes, that if there's kind of a pool logic that you can implement. And so the idea being that if the queue at the pickup window is at 3 cars, then the queue at the order window needs to sort of stop taking orders. And so you need to start like that to start in queuing because there's just not enough space. And I have a video on Canvas to show you how to do that. So if you go to the ARENA help section module on Canvas, you can go down through there, and one of those is a video on how to implement, how to use a hold module when you have multiple processes in series in ARENA logic. So take a look at that. The other general comments I'll make is just make sure that you're asking a question that really warrants simulation. So that would mean that, if you just say, we are testing to see whether adding another barista improves performance. Well, unless you model something really complicated in the layout of the coffee shop, adding another barista is going to improve performance. We don't need a simulation for that. Now, if you tell me that there's limited space in the coffee shop, and so we can either add a barista, or we can add an order station, or we can add maybe another coffee machine or whatever. Like if you can say that there's all these things that we can do, but we can't do all of them, then you set up a really interesting scenario where you can say, okay, we're going to use simulation to compare the performance so that we can say that you'll get a better performance by adding a barista than you will by adding someone in the order station or something like that. That starts to get to something that is more difficult to answer with a standard, 470 type approach, a queuing theory approach, where you might need the simulation. Or these things in the drive-through, how you have a queue that ends up like having a maximum length of 3 before it starts interacting with other queues. That's also something that would be difficult to handle in 470, but would be easy to handle in simulation. So I want you to kind of find something that the answer is not obvious when you ask the question, and you need to do simulation for that. Of course, you shouldn't be too overly ambitious. There's only a couple weeks left after all, but at least find something that makes it clear that you really needed simulation to have an insight into that question. And so the layout here, the project has got this submodel requirement, which basically means that in all of your block diagrams, there has to be something that is complex enough that you'd want to draw a box around it and then form an arena submodel out of it. And so that's just kind of a quick heuristic we use to make sure you're building a sufficiently complex model. If you really only have a create block, a process block, and a dispose block, you can't really turn that into a submodel because your submodel would just basically circle one block. And so, you just put a block around a block and that's not really a submodel. So, so this submodel requirement is something that's just historically been in there as a quick way to ensure that you've got a kind of a rich or a more complex system. The presentations will be due the Wednesday of the last week of class. It's a 10-minute presentation. These are video presentations you will record asynchronously and upload onto Canvas. The presentation grades will be determined in part by peer review. Your final report is also due that Wednesday. That'll be uploaded, the desired format, 4 pages maximum, although you can have an appendix that's unlimited, and some samples. I think I changed the format of the report, and I don't know if I have samples in the new format. I might have taken those samples down, so this might be an old note here, but you can see the desired format. I think it's pretty cut and dry, is on Canvas. You upload that, and again, your report grade will be determined in part by peer review as well. So then how do we get these peer reviews? So by the Saturday before the originally scheduled finals week, so basically the Saturday at the end of the last week of classes, then you will be asked to review a final report as well as a presentation. That's it, just one of each. And you'll submit your peer review by filling out a rubric and then filling in a constructive comment. And then I will grade your peer reviews, and that's how you get your peer review credit. And then I will also grade the final reports and the presentations, keeping in mind those peer review scores. So, so that's how all that grading works. And then I already mentioned that this Canvas Activity M is a sort of best greatest hits of the post midterm Canvas activities. There's then the final exam. Okay, so this is an old instruction. I forgot to catch it here. So remember, this semester, the final exam is a little bit different. We're not having a retake because they're not allowing us to put anything in the normal finals week. So what we're doing is a 2-stage final. So the Thursday of the last week of classes will be just like the midterm. You've got 90 minutes anytime that day to take a final exam by yourself using Respondus Lockdown Browser. And then the Friday of that time, you then get, for 20% of your final exam score, an open book and collaborative experience where you take the exact same final exam again, but you're free to communicate with your classmates, just your classmates, and use your notes and use any resources that are on Canvas. I don't want you finding other resources, no Course Hero, no Chegg, etc. Just the resources that are on Canvas, your notes, and your classmates. And that will be the exact same test you took on Thursday. The individual test will be 80%. The group test will be 20%. For those of you that have too many final exams that last week, of course, I'm giving you the option to go into the people group section in Canvas and then groups. And you can move yourself into the later final exam group where you do this exact same Thursday, Friday setup, on Monday of Tuesday of the original final exam week. So if you want, you can take it a little bit later. You will not have access to the exam on Thursday and Friday. You'll only have access to it Monday and Tuesday. Those of you who take on Thursday and Friday will not have access to it on Monday and Tuesday. So if you're overloaded with exams, you don't have to ask me, you can just move into that group, but you have to do that movement before December 1st. And then on December 1st, I'll actually then assign the final exam due dates based on who's in those groups. So you can adjust your group membership on Canvas by yourself, self-selected. So there's a question in the chat. I wasn't able to find the later exam group on Canvas. Is it supposed to be within the early exam group? So the on Canvas, and I think one person's already done this, so I'm pretty sure it's working. So right now you see me looking over, I'm logging into Canvas. I'm gonna go onto my student view and then I'll pull that over into the shared screen here. So here we are on Canvas. And if you go down to the people right here on Canvas, and then if we go over here to this tab, Groups tab, then you can see under Groups, there are these two groups, early exam and later exam. And because I am a test student, I don't have the option to join this group. On your display, this little lock should say like join or something like that, and it might say leave on this one. And so you can swap from this group into this group. And then, so once you move into that, then you'll see that you'll be in the later exam group. If you like to see who's in the later exam group, you can open that up and you get to see who's in that later exam group. Why would you want to do that? Because those are the people you can take the group exam with. And so those are the people you could reach out to Tuesday of the original finals exam group and say, hey, do you want to work together on the group portion on Tuesday? So everybody else by default is in the early exam group over here. So find that under people and groups. And then there's another question, Monday will be the normal exam and Tuesday will be the group one. That's correct. And so it's exactly the same timing, just shifted a couple of days. And so for the early group, it's like it says here, Thursday will be the individual exam you take by yourself. Friday is the group. In the later group, Monday will be the individual exam, and then Tuesday will be the group. So there you go. Any other questions about that, about the exam layout? Also, while I've got Canvas up and on the sharing here, I've added a course evaluations here. If you click on that link on Canvas, which is also found under modules and then under course information, if we expand the course information, then there is a student evaluation of course right here. That will be available until November 27th. And so if you'd like to provide feedback on the course, then you can do so via the course evaluation link here or down here. And I think you should also receive emails about that. That's the standard Fulton Engineering course evaluations. All right, so I'll put that away over here. All right, so any other questions about the final exam or about the timing of things? I'll go to the question slide here. All right. Okay, so let's move on. And so, so what we have been trying to motivate from here on out is the lack of use of point estimators. So this is a reference to Point Break, which back when I was younger, this was the Point Break movie that was out, but now there's been remakes of Point Break that don't have Keanu in them or Patrick Swayze. And so the idea is you want to break your point estimator habit. You're always tempted to give point estimates, single estimates, but interval estimates are where it's at. And so I mentioned last time that even when that interval estimates trickle into your other statistics as well. So when you're, for example, fitting a linear regression line, the slope of that line is itself an estimate, and it's tempting to give its point estimate, which is this thing up here. But in reality, that point estimate, this line, it could be, this is kind of your estimate of the slope of the line, but the real line might actually be this way or might actually be this way. And if you took different data, then this line's slope might vary from experiment to experiment. And so for this experiment, the best fit line was these, but like I said, the real line, the real relationship between the independent and the dependent, the independent and the response variable might be slightly different. And so the slope of this line is itself something which needs an interval estimate. And once you have an interval estimate of the slope of that line, then you can say things like, is it significantly different from 0? And if it is, then that means you found a relationship between your independent variable and your response variable, or your independent and your dependent variable. And then further on, if it's significantly different from 0, you can also test other things. Like, so there might be theories that in this particular case, which is from natural science, there was a theory. There are two theories. One, that this response variable should scale isometrically, so with a slope of 1, or it should scale with a slope of 3/4. And so by giving me this confidence interval, I know that the slope here is probably not going to be exactly 1 or exactly 3/4, just due to the noise in the data. But this confidence interval allows me to see that from these data, then this slope is quite possibly 3/4. That's one alternative hypothesis. So it provides support for that 3/4 hypothesis, but it is definitely not 1. So it rejects that hypothesis. So I've rejected the hypothesis of 0, I rejected the hypothesis of 1, and I have not rejected the hypothesis of 3/4. And so if you had a bunch of different papers that took different data from different experiments, and they all failed to reject the hypothesis of 3/4. And as they took more data, this confidence interval would get narrower and narrower. And if it kept collapsing and yet still always included 3/4, then our hypothesis of 3/4 becomes a theory, just like we have the theory of evolution by natural selection. So that theory is a very, very well supported hypothesis. So it is something that you've just not been able to reject, is that it's always consistent with your data. And what do we mean by consistent with data? Well, with a lot of data, it means inside the confidence interval. So confidence intervals are what people are going to look for. They are really where it's at. So we have been using confidence intervals to evaluate and are there any questions about this interpretation? Does this make sense to everybody, this confidence interval idea? And if there are questions, maybe I can put up my handy dandy questions slide here if you're shy and would not like to ask a question directly. So any questions about this? Is this pretty clear what this mixture of linear regression coefficients and confidence intervals together? Your boss, the first time you take a job and gives you a bunch of data and you want to analyze, I'm sure will be impressed if you come out and you present them with a confidence interval. So distributions matter and confidence intervals matter. Interval estimates are always better than point estimates. Okay. All right, so we've been using confidence intervals up to this point to do the absolute performance analysis of one system. And so this is like, how well do I do when I build a system where I have 3 operators doing billing and 4 operators doing tech support? And so I've got one system that has its own sample mean and its own sample variance. And so a lot of you have asked how much questions, at least in your initial, so if I were to write that out here, I probably can't write that. So a lot of you in your proposals started to do how much questions. And so how much research questions are really absolute performance questions. You're saying, if I were to implement the system this way, then how much of a performance increase am I going to get? That requires you to have an extremely accurate or I'd say extremely precise and validated simulation. Your simulation needs to be a perfect model of reality in order to really answer this quantity. In order to say to somebody, you are going to make $1 million more a year if you make this change to your system, exactly $1 million worth a year. Like, if someone says, I will not make the change you suggest unless it makes me $1 million a year, and you come back with your simulation, say, look, my simulation made you $1 million more a year, you better be darn well sure that your simulation before the modification perfectly matched the real system. Like the confidence intervals on your simulation must be tight and include the real system in them. Because if they don't, then the $1 million that you infer that you're going to save them in your simulated system is just made up money. It's like monopoly money. It's fake money. It might be you only save them $100, but your system is just not well calibrated. And so the $100 that you save them in real life, it looks like $1 million in simulation. So how much questions, typically they are important and we do use them in real life, but they usually require far more than 2 weeks of time to build a simulation and calibrate them. So that's why the relative performance, which is we're about to get to here, is going to be probably more practical for the questions that you're going to ask during your final project. So, but when you do these absolute performance measures, I'm sorry, you've got a question here. How about if we have a 95% confidence interval that will make $1 million? So that's a great question. So the question here is, well, what if we run our single simulation of our as-is system, and or even our change system, and we say, well, what are your savings going to be? And we get a 95% confidence interval that it's going to be $1 million. Well, but again, before you can say that your change system, you can trust that confidence interval from your changed system, you need to make sure that your changed system is a good estimate of or that your as-is version, so without your changes, is a good representation of the real system. So you're going to need to make sure that the real system's confidence interval includes, or that the confidence interval of your as-is simulation includes the real system, and the confidence interval is tight. And so it's kind of this tightness that if you're to sort of say that I managed to build a calibrated system that under a wide range of inputs that come from the real world, I always track the performance. And tracking like if you have a giant confidence interval, so if your confidence interval, goes from, 0 to 1 million, so it's a giant confidence interval from 0 to 1 million, then that's not really, that isn't really going to hold up in validation, because if the actual profits were 500, but the confidence interval goes from 0 to 1 million, then I just can't really trust that confidence interval because it's just too wide. If the real system is 500 and my confidence interval is plus or minus, $5, then I've got a good idea that my real system matches my simulation system, especially if then I run a new set of inputs through that I could do my calibration with one set of data, and then I can run a set of test data through my system. And if my simulated system moves in the same way my real system did with that test data, then I'm pretty confident that my as-is system is a good representation of my real system. So you need a tight confidence interval in the as-is system. And then in the real system, sure, you can say that my real system, or my intervention system, my new system, has a giant confidence interval, and it does include some really amazing results in that confidence interval. But when you present it to your stakeholder, they're going to look at the entire confidence interval, and they're going to say, yeah, it might be that we make $1 million, but the other half of your confidence interval suggests we could actually lose $10,000. And your confidence interval doesn't discriminate between the two of them. So really don't look at your confidence interval as focus as much on what's outside the confidence interval as what's inside the confidence interval. So what you really want to do first is ask, does my confidence interval include 0? So if I have a confidence interval that that represents the change between my systems, and this is really getting to relative performance, then I say, does it include 0? If it includes 0, there's a chance that I made no change, and there's a chance that I actually did worse or better, but I can't tell the difference. If your confidence interval does not include 0, then you can be confident that your system is better or worse. But again, that's really kind of a relative performance measure. So again, on most of these systems, relative is going to be easier to make a convincing story of than absolute. And if you've got large confidence intervals, for an absolute performance measure, there's not a whole lot you can do with that. Unless you're just purely trying to show that even though we have a giant confidence interval, we're guaranteeing you that you'll make at least $5 or something like that. As long as 5 is outside of that confidence interval, then you're okay. But you can't really tell them exactly how much they're going to make. It could be $6 if that's where the confidence interval ends. So it's a little bit more of an art than a science, but pay attention to as much as how much it's outside the confidence interval and inside the confidence interval, and try to make as tight as confidence intervals as possible. Large confidence intervals, you just can't really make much arguments about. So I know that was kind of long-winded, but and it also sort of kind of required me to invoke relative performance to answer, which again suggests that relative performance is just going to be an easier thing for you to work with. All right, so oh, good. I'm glad that made some sense. I wasn't sure it made a lot of sense as it was coming out, so I'm glad it made sense as it was received. So yeah, absolute confidence intervals, you know, I kind of beat this over the head here. We have a hypothetical that we are testing over here. So this is like, you know, in my system where I've got the separate operators for tech support and billing. Then I want to know under this configuration, what is the possibility that I'm going to make, you know, $1,000 a year? And if $1,000 a year is your hypothesis that you're testing, then the confidence interval that comes out of your system is saying that you're going to make more than $1,000 a year. I can't guarantee how much you're going to make. I can give you a point estimate if you want one, but in reality, I don't really have any confidence outside of this interval. But I know that it's going to be more than your hypothesis because the hypothesis is outside the interval. So, so I don't know anything inside the interval. It's going to be one of these, but it's not going to be that, at least with 95% confidence. So that's what you can do with an absolute confidence interval. But relative is often going to be more convincing. So in this case, you're saying I have my as-is system where I train people separately for billing and support, and I have a separate bank of billing support reps and support reps. And then I could propose that I want to do cross-training and just train them all for both. And maybe that will help deal with the fact that I get so few people going to billing that my billing operators are sitting idle. So rather than reducing the number of billing operators and increasing support, which may not help, you know, at certain times of the month where I get a surge in billing calls, then I could say, well, what if I just cross-train both of them and have one type of operator? Then how well is my performance going to go? And now I can compare the two of these. And I don't need to worry about whether I'm absolutely correct. All I need to worry about is, did I get an improvement from one simulation to the next? And if I get an improvement in simulation world, then hopefully I get an improvement in the real world. I don't know how big the improvement is necessarily, but I know there is an improvement. And so there are there are several ways that I can do relative performance estimates. And one way that I can do that is to run the same data. So in this case, the same callers into both systems. And for you know, one stream of callers, so I take all the callers that occurred on a Monday, and I put the Monday callers in here and the Monday callers in here. And then I look at the performance coming out of the system. And then I do all the callers for Tuesday, and I do all the Tuesday callers in here, all the Tuesday callers in here, and then look at the performance difference. And so each day I can view as a different comparison between performance. You can say on Monday, system 2 did a little bit better, but on Tuesday through Friday, system 1 did better. And so by comparing them apples to apples with the exact same inputs, I get a better idea of how much of the variance on their output was due to the inputs being different as opposed to the systems being different. So by holding the inputs the same across the two systems, by doing a so-called blocked experimental design, where I create blocks where both simulations get the same inputs, and I create one performance metric per block, which is the difference in performance per block, then I can get more statistical power. And that's what I do here, is I am going to use, for example, the same random number seed for both simulations. And so we'll talk about this coming up here when we talk about common random numbers, one of the last things we talk about in the class. I can go into Arena and guarantee that every time I run 10 replications of one simulation and then 10 replications of a different simulation, that for those 10 replications, every replication across, the first replication in both will have the same random number seed. The second replication in both will have the same random number seed. The third will have the same random number seed. And that creates blocks. And then in those blocks, I can compare performance across the blocks. And that's what we're talking about, doing here. Or in your homework G3, we took real data from a real world system, and then we use that instead of a random number generator in the simulation system. And that created a block across the real world and the simulation, so I could compare the two of them for validation. So why do you create blocks statistically? How does that work? Well, it turns out that the variance in the difference in performance, if you do a little bit of math, is equal to effectively the variance in one system divided by the number of replications, plus the variance in the other system divided by the number of replications. So this is why replications matter, because that reduces variance, but then minus any correlation between the two of them. So if I can create correlation in the outputs across multiple replications of a simulation, and as a system and a test system, if I can create correlations across the two populations from, so replication, replication one, as I go across my replications, if replications tend to be higher or if outputs tend to be higher in one system, they tend to be higher in another, that correlation will end up subtracting from the variance in the difference estimated across those systems. And that gives me more power, so I can get tighter confidence intervals with the same number of replications. That's the magic of paired designs. And so with that, just like you did in the homework, you create differences across your blocks, and then each block difference is independent from each other block's difference. So I can then run a one sample t-test on the differences to test whether they include 0. And if they include 0, we conclude that we can't tell a difference between the systems. If they reject 0, then we can conclude that one system is better or worse than another. And so this is just documenting that, where the standard error of the mean, the formula there is just the standard deviation of all the differences, just like you did on the homework, divided by the square root of the number of replications, just like you did on the homework. And the degree of freedom for your t-test is just the number of replications or the number of blocks minus 1, just like you did on the homework. And then you can calculate a confidence interval based on this standard error and this degree of freedom. So the degree of freedom goes into your critical t-value, the standard error of the mean is scaled by the critical t-value, and then that gives you a half-width around the estimated mean. And that is your paired your paired difference confidence interval. So that is one example of a way to do a relative performance confidence interval. Now, sometimes we can't do blocking. So are there any questions about that? What I mean by blocking, we've created statistical blocks, and then that created a difference across every replication. So if I were to say I've got replication 1, replication 2, so this is replication 1, replication 2, replication 3, and that's going to give me some performance for system 1, some performance for system 2, and some difference, which will be the performance difference between them, P1 minus P2. And you can repeat that for all of your replications. So these are your replications. And then that will give you that many replications of differences. And we're going to just do a one sample t-test on those differences. So that will give us a confidence interval that we can compare to 0. So we can ask, is 0 in that confidence interval? That is the blocked design or the paired difference t-test. Are there any questions about that? It's identical to what you did on your homework G3. And the ARENA's output analyzer can actually do this pairing for you once you've generated the replication. So you can bring them in and you can tell it, I want you to do a paired difference test. Okay, so then the alternative is sometimes you can't block your two simulations. Maybe it just doesn't make sense. They're just fundamentally different. And so even though you can set them up with the same random number seed, because the processes are so different, you're drawing a different type of random numbers, you're drawing more random numbers. There's no way to create a correlation across the outputs. There's no way to say that. So this would be the case where you can get, let's say you say one set of systems is optimized for drip coffee and the other system is optimized for espresso-based coffee. And so you get a certain set of customers in, and sometimes those customers want more drip coffee, and sometimes those customers want more espresso coffee. Now, if it was the case that more espresso coffee is always going to lead to a longer performance or a slower performance, then we could do the pairing and create that nice correlation between these. But it might be that the things that are hard for one system are easy for the other, or vice versa, in which case you have the wrong type of correlation for the paired design to work, and you have to treat them then independently. So in that case, you run an independent set of customers into one system and an independent set of customers into the other system. And that way we have independent samples. Samples from one system are independent from samples of the other system. In that case, we then need to run a proper two-sample t-test, but we can generate a confidence interval that captures the two-sample t-test as well. And so there are two ways to do that. And one of the ways is a so-called pooled variance two-sample t-test. In this case, we assume that across my two system types, my separately trained and my cross-trained, for example, across the two different systems, if we can make the assumption that the variances are the same, then we can calculate the variance across the entire group. And that will give me a better estimate of my variance and will give me more statistical power. So we're not going to calculate the means across the two groups. We're going to calculate the variances across the two groups. So that's when we're pooling. We're putting them all into the same pool in order to estimate the variance from those two groups. How can you justify this assumption? There are tests like the F test or the Levine's test. So you can run tests and you can Google for these tests. Like, what are good tests to test to see if two populations have the same variance? And so you run a Levine's test or you run an F test, and you're able to then justify that these two populations, coffee shop 1 and coffee shop 2, have the same variances. In that case, you can pool them together and run this pooled variance t-test. And so what do you do in a pooled variance t-test? You can calculate the variance, and there's a formula here for variance, which this is the variance of system 1, this is the variance of system 2. So you can estimate their variances separately, and then you can scale them by basically the number of samples in system 1 and the number of samples in system 2. And so if you think back to how variance is calculated in the individual system, then this what you end up kind of doing here in the numerator of your pooled variance is you're kind of getting rid of the scaling that was in your original variance calculation for the original systems. And then you're rescaling them by the total degrees of freedom across your pool of samples, as you pooled all of them together. And this will give you a pooled variance. Now, you lose 2 degrees of freedom because you have a mean that's estimated from one system and a mean that's estimated from the other system as well. So this 2 here represents the 2 different systems. So when you calculate the variance across the pool, you have to divide not by the total number of samples in the pool minus 1, but the total number of samples in the pool minus the number of systems that you pooled. But otherwise, it looks just like a standard variance calculation. And once you have this pooled variance, there is this nice formula for standard error of the mean. So the mean that we're trying to estimate is this difference between the mean performance of the two systems. And with a little bit of math, you can say that a good estimate of the standard error of the mean, assuming normality and assuming that their variances are equal across the two systems, is the standard deviation of the pooled system scaled by this number here, which is just 1 over the number of samples from the first system plus 1 over the number of samples in the second system. You put that together, and then that gives you the standard error of the mean of the pooled system. This works well for low sample sizes, if you, but you have to assume that across your two systems you have equal variance. So if you can use this pooled variance, you should do that because it has a lot of statistical power, because you're able to get a tight variance estimate even though you have a few number of samples. So with that, you have a degree of freedom and you have a standard error of the mean. That's all you need to calculate a confidence interval, is degree of freedom and standard error of the mean. And then you can end up using that. So you basically calculate this as the center of your confidence interval, just the mean from system 1 minus the mean from system 2. And then you then put that confidence interval around it, which is always going to be the formula, which will be the critical t-value with this many degrees of freedom, and whatever your significance level is, almost always 5%. And then that critical t-value scales the standard error of the mean. That's what gives you your half-widths. So this is effectively a formula for your half-width. Now, the other case that you have to worry about is, what if I can't pool? What if one system has a different variance than the other system? And that is, you need a so-called Welch's unequal variance t-test. And in the Welch's t-test, and sorry, I was looking at a private message here. So the Welch's t-test, then there is a different formula for standard error of the mean. So the standard error of the mean in the Welch's t-test is just the square root of the variance from the first simulation plus the variance from the second simulation. So it's a very, very simple expression for the variance of these two systems. It's effectively just the sum of the two variances, because we assume that the two simulations are independent from each other, so we can add their variances. So the standard error of the mean is going to be very easy to calculate. So there's a question. Could I explain a little bit more what standard error of the mean means generally? It has different functions and formulas based off the test. So yeah, it's not the test so much as the assumptions about the data. So standard error of the mean, in this case, always means if I were to calculate this value, which would be the mean value of one system minus the mean value of another system. If I were to run an experiment and calculate that value, and then rewind and rerun that experiment and calculate that value again, and then rewind and rerun that experiment and calculate the value again, I could do that 1,000 times. And over that 1,000 times of running that experiment, I would get a different mean value every time. The standard error of the mean is going to change reflects the width of the distribution of those mean values that I estimate every time I run the experiment. In practice, you only run the experiment once, but I need to estimate how confident I am that the mean estimate that I got out of the system is close to the real mean. And that's what the standard error of the mean tells you, is it tells you how nearby, basically what's the variance on the experiment. Now, it's not the t-test that is changing the standard error of the mean. What's changing here is the relationship between the two systems. If the two systems if the experiment has been designed so that the two systems are blocked so that there's a correlation in their outputs, that necessarily means that the variance on the mean estimate of their differences is going to be tighter than it would be if they were independent. And that's why the standard error of the mean for the paired situation requires a different formula. If instead they are independent simulations, but they have the same variance in the two populations, then the standard error of the mean will be a different formula. If instead they are independent simulations, but they have different variances, then the standard error of that mean will be a different formula. So there's three situations I can be in. Either I've designed the experiment so that there is correlation in the outputs, so that when I subtract the outputs, I actually subtract off some of the variation. And that means that my mean estimates are going to be tighter just naturally. Or they're independent simulations with the same variance. Well, then I'm going to have a certain variance of my estimator. Or they're independent simulations with different variances, and then I'll have a different variance of my estimator. And these different formulas for standard error of the mean estimate the distribution of those. So if I were to, so every time I calculate a mean, so if I've got, this is my mean estimate, y1 minus y2 minus y2. And this is my mean estimate. So I take the mean of both of those. So at every simulation, I get a different mean estimate. So sometimes they're close together and sometimes they're far apart. If I were to then take a histogram of those, then this standard deviation here, so this ends up giving the standard error of the mean. And this width, I'm trying to draw an M here, but my mouse pad ran out of room. So this standard error of the mean is the width of the distribution of my mean estimators. And that width will change depending on how I design my experiment. And we have to use the correct width when calculating our t values. So in some ways, so it's like different t-tests are designed for different populations. It's not that my confidence intervals differ by t-test, it's more like my confidence intervals differ by population. Or in other words, I have to use a different t-test for different populations. Does that make sense? Okay, looks like it makes sense. To clarify, there are three types of tests we can use for comparison of two systems. A one sample t-test, a two sample t-test pooled, and a two sample t-test unpooled. That is correct. When I'm comparing two systems that are normally distributed, there are three ways to compare their means. The paired way, but I can only do that if I've blocked the experiment so that I create these experimental blocks, or the two sample ways, one with a pooled variance, which use pooled variance if you can, because you have higher statistical power. But if you cannot count on their variances being the same, use the unpooled, Welch's t-test. And this also comes into account when you consider more than two systems. So if you were to go and look up the ANOVA, which you hopefully remember from 385 or 380, the ANOVA itself is kind of like a t-test for more than two groups. In fact, that's exactly what it is. And the ANOVA, by default, assumes equal variance across groups. If you have unequal variance, you need to make sure that you use an ANOVA that is designed for unequal variance. Most statistical packages allow you to choose an ANOVA with unequal variance, and it will do the proper corrections for you. If you do pairing, so you create a pairing across things, there are ways to also design your ANOVA to account for that pairing. But you have, so however you design your experiments, you have to use the proper test, because tests make assumptions. A one sample t-test has certain assumptions. A two sample pooled variance t-test has certain assumptions. A two sample unpooled variance t-test has certain assumptions. You need to make sure that the assumptions match the test. Okay. Any other questions about that? Okay. All right, so unfortunately for the unpooled test, the degrees of freedom is a really ugly formula, and it's beyond the scope of the class for me to explain where this degrees of freedom comes from, but it's just a good formula to know. So if you have an unequal variance, so an unpooled data set where you have to calculate the variances separately, the standard error of the mean is very easy to calculate, but the degrees of freedom is ugly. But once you calculate it, then you can get you can get your 2-sample confidence interval, your relative performance confidence interval. This has lower statistical power, but as long as you have at least 6 samples in both populations, it should work okay. If you have under 6 samples in both populations, then you probably just need more data. If you have unequal variances across your 2 populations and you only have 5 samples from both populations, there is no way you can characterize the variance in your full system, and you just need to gather more data because you're not going to be able to make a good inference about the relative performance of these 2 systems. It's like having a fair coin and an unfair coin and flipping them 3 times each. You're not going to be able to tell a difference between your fair coin and your unfair coin with only 3 flips. There is no test I can give you that can tell the difference between those 2 coins. You just need to flip both of those coins more often. Okay. All right, so for all 3 cases, you use the correct formula for standard error of the mean, you use the correct formula for degrees of freedom, you then calculate the mean, the difference in means, which is the mean difference, and then you calculate the confidence interval using the critical t-value with the degrees of freedom that you calculated, scaling the standard error mean with the formula that you calculated earlier here. And then with that, you're going to get a confidence interval and you'll be able to compare it to 0. If it includes 0, then the systems cannot be told apart. That doesn't mean they're equal. That just means with the number of samples that you have, you can't tell the difference between the 2 of them. The difference might be buried. It might be so small that it's just not detectable with that many number of samples. If 0 is outside of the confidence interval, then depending on where the confidence interval is, purely positive or purely negative, you can then make the inference that one system is better or worse than the other system. And that's what I'm sort of summarizing down here. So questions about how we use 2-sample confidence intervals. Okay. All right, so this is all of that summarized in one slide. So this is a great slide to sort of just have as a quick reference because I've got the paired difference degrees of freedom and standard error of the mean. I've got the pooled variance degrees of freedom, standard error of the mean. I also remind you that you can do a Levine's test to test for homoscedicity. So homoscedicity is the condition of equal variance. So if you have equal variance across the populations, you can use the pooled variance. You can use the Levine's test for that, an F test, a number of other tests. I say the Levine's test has probably got the highest statistical power. So for very few samples, probably go with the Levine's test. That's my opinion. And there is your degrees of freedom and your standard error. For the unequal variance, where you can't pool them, you would effectively use a Welch's t-test or a Welch's ANOVA. And this is low power, so you need at least 6 in both populations, but you don't have to have many assumptions. And this is the degrees of freedom, and this is the standard error formula. So all of those on one slide for you. Notice as you climb in assumptions, so no assumptions down here, some assumptions here, a whole lot of assumptions up here. As you climb up in assumptions, you also climb up in power. And so that is the magic of assumptions, is that they give you more statistical power. With more assumed about the fundamental system, you need less data. And that comes out as having more statistical power for the same number of samples. And then I've got some examples here from real studies. So this is a study from another colleague out in California where she had to do a comparison between 2 populations. And these, so she just listed her 2-sample her paired difference confidence intervals right in the text. So she said here that that this, I'm not going to go into the details on what the data sets mean here, but in this data set, Lilith 2, then she lists a t-test, a paired difference t-test, where she said it's a paired test, there's a paired difference t-test. She lists the mean difference here, and then she lists a confidence interval. And you can see that confidence interval, it's negative on one end and positive on the other end. So this confidence interval includes 0, and that is identical to saying that the paired difference t-test is not significant. That's what she's saying. So these are two things saying exactly the same thing. In a different population or a different set of populations, so which we're calling Hermione here, then she does the same thing where it's a paired difference t-test where the mean difference she gives here, but then she lists the confidence interval and it straddles 0. So because it straddles 0, the paired difference t-test is not significant. But then down here, she's got significance where she lists that in her paired difference t-test, she's got her confidence interval listed and it's purely negative. And purely negative confidence intervals on a paired design means you're not including 0, which means that is a significant result. And so P is less than 0.05, and that's what she's listing here. So she's listed both the t-test results and the confidence intervals just to be complete, but really you only need one, and they always agree with each other. Likewise, this is from a colleague here at Arizona State, that in his case here, he ran an experiment that he designed. So I work with ants in some of my work in bio-inspired engineering. And so I have a lot of ant examples. And so he had these number of ant colonies in his lab, and he ran them all under 2 conditions. So each colony ran under a condition of 1 wall and 2 walls. And the X's are the 2 wall data, and the O's are the 1 wall data. And so for this colony, you can see that 1 wall had a higher shift than or 1 wall had a lower shift than 2 walls. The same for this colony, the same for this colony. So by visualizing this way, I can see that in almost all of the colonies, the X's are above the O's. So that kind of tells me that the particular difference varies. So in colony D, there's not much of an effect. In colony A, there's a moderate effect. In colony E, there's a huge effect. But the effect across all colonies, except for maybe 1, is positive. And so that implies to me that there actually is an effect. So I am controlling for the variance across the colony by giving every colony both treatments, by creating a paired design. And so he did a paired t-test across these, one-tailed, and found a significant difference. And so, and then there are other ways that you can plot these things. So this here is another paired example here where they looked at differences in populations. And here they're just showing that that they're plotting the difference. Okay, sorry, in this particular case, I'm showing for these independent ones, these are 2 samples, these are not paired. And so I've got one population that is young and one population that is old. And in this case, I'm just plotting effectively the 1 sample confidence interval and the other 1 sample confidence interval, and then running an explicit 2 sample test on them. So that's just a comparison between when you can run a 1 sample and when you can run a 2 sample. If you want to do all this in the output analyzer, ARENA gives you tools for doing that. So you can bring in multiple data sets into the output analyzer, and under the analysis menu, you can run an ANOVA. And in that ANOVA, you can adjust all sorts of settings. You can do Bonferroni correction like we talked about before. You can adjust the confidence level, and then it will even show you your 3 populations with their box and whiskers plots. And it will then even rank them so that you can see which systems are not distinguishable from each other. So these 2 systems are the same, and which system is distinguishable. And in this case, if this response variable, if higher is better, then this would be the best system. And these 2 systems can't be told apart but they're both worse than this system. And so that can be done. This is inside the process analyzer here. It'll do that for you. So you can run the ANOVAs in the output analyzer. You can do these comparisons in the process analyzer. And I think you'll have experience with that in both labs and lab. I think in lab 9, it flirts with that, and then also in lab 10. So I think I'm going to skip a lot of this here just because I'm running a little bit behind. But if you were to flip through these slides, I basically go into what happens when you have more than 2 systems. And I go into that here. So I have to worry about the multiple comparisons problem, which we've already talked about briefly before. I also mentioned that in ARENA's output analyzer, it actually has the Bonferroni correction that you can select. So if you have multiple systems, you can tell it to use a Bonferroni correction so that when it compares across them, it properly adjusts the individual test confidence level so that the family confidence level is 95%. The other thing that I talk about in these slides, if you were to flip through here, is that if you ever look at the output of an ANOVA, you may notice that there's little letters that pop up outside the ANOVA groups. And these letters represent which groups you can tell the difference between and which groups you can't. And so if you have multiple treatment groups, each one of these you can view as a box and whiskers plot of the data from each individual group. And what these letters mean here is that anything that shares a letter is not significantly different from anything else that has that letter. So these 3 all have an A in their group, which means if I were to compare this group to this, or this treatment group to this treatment group, the p-value would not be significant. So anything that shares a letter is not significant, not different from each other. But if they don't share a letter, like this B up here, this group, which is the 24-week group, it has a B, and the 6-week group only has an A. So there is a significant difference between this 24 group and this 6 group. So these letters that annotate an ANOVA come from what we call a post-hoc test. And so this particular test is what's called a Tukey test. And so inside ARENA's output analyzer, you can ask it under comparison method, instead of selecting Bonferroni, you can select Tukey, and it has a higher statistical power way to do these comparisons. So the Bonferroni was kind of back before the Tukey test existed. You can do the Bonferroni correction, which we've already talked about before, which is kind of a crude way to do these comparisons between groups. But the Tukey is a much higher power version of this, so you can get much better results with fewer samples. And in the output analyzer, under that comparison, you can select Tukey, and it effectively does all this for you. So I know I'm kind of going through this a little bit fast. These are just kind of auxiliary things that I at least want you to have exposure to, because in the real world, you're never going to see an ANOVA alone. The ANOVA will always have these annotations on top of it, which represent which group is significantly different from which other group. And that's all I'm kind of summarizing with this kind of bonus information here. And then you'll have experience or exposure to OptQuest in Lab 10. OptQuest is a really amazing tool that I recommend you give a shot in the homework and in the lab if you give it for Lab 10. All right, so that is all of the old material. Before we then start into the new material, which of course we'll then have to continue next lecture, are there any questions about any of that? I primarily want you to focus on the difference between absolute and relative, or in other words, 1 data set and 2 data sets. I threw in the additional info about 3 or more data sets because you just should have some exposure to that. But on tests, I'm primarily going to focus on asking you about absolute performance, where you only got 1 population, or relative performance between 2 different populations. I might throw in a Bonferroni correction question in there because we've talked about that before, but all this stuff about Tukey tests and ANOVAs and all that, I'm probably not going to ask you about. So primarily those are the 2 things I'm going to be focusing on. So any questions there about relative performance, about these 2 sample confidence intervals, any of this stuff, before we move on to the totally new unit? Okay. All right. Maybe we'll do an attendance exercise just to keep everybody awake. So I'll put that link is in the chat, and the attendance exercise question that I will ask is what does the Welch's t-test enable you to do? So what is special about the Welch's t-test? So that's the question. Again, this is graded for completeness, not correctness. So I put the question in the chat, and I put the link to the attendance exercise there in the chat. All right, so we are now moving into Unit K, which is all about variance reduction techniques. I've already talked a little bit about variance reduction techniques. In Unit J, we primarily focused on how do we choose the number of replications that we need to run based on the variance that gets spit out from our systems. So we run a pilot experiment, and it gives us variance, and then based on those variants, we decide how many replications we need to run of our simulation to get confidence intervals that are appropriately tight. So now the question is there a way that we can redesign our simulations so that they fundamentally have less variance? This is very closely related to the paired difference t-test that I just talked about there, where if you can pair two simulation types together in a relative comparison, you can reduce the variance in their difference. And so that's what we're going to say is what are general ways for us to reduce variance? And so we are going to use control. So when we refer to control in experimental methodology, that means accounting for sources of variance. So when you run an experiment, a simulated experiment or an experiment in a real factory or whatever, people will ask, how did you control for the effect of different states' policies about, I don't know, COVID-19 lockdown or something like that? So if you're trying to make an inference about the reproduction rate of COVID, and you say, and I took data across the entire United States, then someone will say, well, how do you control for the fact that New York might be different than Ohio, that might be different than Arizona, that might be different from California? And what they mean by that is as you go from state to state to state, the different policies in the different states introduce a source of variance. And so I can't actually pool across them. So how do I control for the variance that's introduced by the fact that I have different states? So control means accounting for variance. And so how do I design my experiment to somehow not allow for potential sources of variance to create variance in my output? That's what control is all about here. So I give some examples here just for motivation. I might skip some of these because I've been running so slow in my rate lately. So this was just kind of a nice study that came out last year that I got excited about and added these slides in last year. Normally I would jump right to this slide, which is suggests that there are 4 different ways that we go over how we control the variance in our simulation studies. And so these are ways that we are going to, in a smart way, introduce bias. So normally we would want to remove bias, but in this case we can actually introduce bias. As long as we know how we're introducing it, we can account for it. And if that bias reduces our variance, then that is a good thing. Leverage correlations, we've already seen kind of an example of that. So we can introduce correlations between variables, and that will reduce variance, or correlations between samples in order to reduce variance. So we're going to do these techniques of toying with the design of our experiment to reduce its variance so that we can get better estimates with fewer samples. And the 4 ways we're doing that, I name here as common random numbers, control variates, antithetic variates, and importance sampling. And I am going to start with common random numbers and control variates, and then we'll move on to antithetic and importance sampling. I think I'm probably just going to dip my toe into common random numbers today, and then we're just going to have to cover the rest of these next time. But I normally cover all four in one lecture anyway, so I'm not too worried about that. All right, so common random numbers. This is very closely related to the paired difference t-test we just talked about. And so in this idea, which is also known as correlated sampling, matched streams, or matched pairs, I'm just going to use the same random number seed for for every replication of two different types of simulations. So I'm doing a relative performance estimation, but I'm effectively running the same inputs into both simulations. And by running the same inputs into both simulations and then comparing their performance for the same input, I'm effectively controlling for the variance across different inputs. By giving the same inputs to two different systems, and I subtract off the performance for the same input, that allows me to really say that the difference between the systems is due to some fundamental difference in the systems and not due to the lucky break of one system got an easier input than the other system. So that's what we do with common random numbers. And it makes use of the same thing that I've already talked about for the reason why we do paired difference t-tests. I introduce a positive correlation in the performance metrics, and when I then do the mean of the difference in those performance metrics, that I end up taking away variance that's due to the variance in the inputs. So if you think back about the muffin baking oven, then I had two policies, greedy and nearly full. Now, in that muffin baking simulation that I had you hand do back in lab 2, you ran the same muffin schedule through both policies. And that allowed you to control for the effect of muffin schedule. So some muffin schedules are just going to be better than others. And if you were, if it might be that if you just did random schedules, you might just do an easy schedule for your greedy test and a hard schedule for your full test. And it's going to look like your full test is worse than your greedy test, when in reality, it was just bad luck in how you chose your inputs. So by running the same input into both, then it allowed us for control for the difference in inputs. And I will pick up where we left, or where we are here next time. I don't want to hold you over for any longer. So let me give you one last attendance exercise, then I'm happy to stick around for a couple of questions. So there is the last attendance exercise prompt. And the question here is, if we cannot reduce the number of samples, how else can we reduce the width of our confidence intervals from simulation? And so this kind of goes back to the title of this unit. So I put that question in the chat, and that's all I've got for you today. So if you have any questions, I'd be happy to take them. Otherwise, we will pick back off in VRT, Variance Reduction Techniques, on Thursday. All right. Looks like we're getting some folks dropping off. Still a quorum in the participants list though. All right, looks like everybody's heading out. In that case, have a good week. See everybody Thursday.